Hello everyone. I'm Pranali Surkar. I'm working as an assistant professor in the Department of Electronics and Communication Engineering at Marri Laxman Reddy Institute of Technology and Management, Dundigal, Hyderabad. So I welcome you all for the video lecture series on the course Digital CMOS IC Design. So we have already discussed some course objective and course outcomes and whatever the syllabus is there for this particular course that we have seen in the earlier lecture. And I have given some brief introduction about the introduction of IC and what is meant by IC and what is the CMOS. So I have given some structure about the NMOS and PMOS and CMOS as well. So this was the just the introductory part, but now we are going to continue from the unit 1. The unit 1 is nothing but introduction to IC design. So these are the contents of the first unit. So here we are going to see the historical perspective, and in which we are going to see who has invented the IC, first IC, and how this electronic era of electronics started with the solid state. So next we are going to see what are the design issues the manufacturers or designs face whenever they want to design some integrated circuit. So these some important issues we are going to discuss. Then we are going to see the quality matrix, means on which factors the digital design is depends, and what are the components or what are the some parameters on which quality depends. So after that we are going to see some MOS. Again in detail we are going to see some MOS structure, and again we are going to see some fabrication process also includes on PMOS and NMOS, as well as CMOS fabrication technique and fabrication steps also we are going to see, and the BiCMOS, which is the combination of bipolar and CMOS, means MOSFET. This technology also we are going to see, and after that we are going to see some VLSI design flow, front end and back end. We will see in the details. MOS layers, stick diagrams, which is the cartoon of the layout, means whenever the designer wants to design the layout of the circuit, he has to first go through the stick diagrams. So how to draw the stick diagrams, that we are going to see in the first unit. After that, for layout designing, some design rules we have to consider. So some lambda based rules and micron rules are there for the designing purpose, that we are going to see here. After that we will see some NMOS and CMOS transistor layout diagrams, in which we are going to see the inverter layout, NAND layout and NOR layout, and some gates also. And the last topic in the unit 1 is scaling of MOS circuits. So in today's class we are going to focus on the historical perspective. Then we'll discuss some issues, 10 issues we are going to discuss here, and some quality matrix. So as we are starting with the integrated circuit, we have earlier discussed about the definition. Again, I'm here just brushing up the knowledge of integrated circuit. So we have seen that integrated circuit, we can call it as microchip, or simply chip we can call it as. And this integrated circuit, which is the fundamental building blocks of any modern electronics, in which we are going to interconnect some billions and millions of transistors, and some active devices and some active and passive components like transistors, resistors and capacitor. We all are interconnected on a single piece of semiconductor. Typically we are using the semiconductor as a silicon here to perform the specific functions. So this is nothing but the integrated circuit, which is the crucial part of any electronic circuit. So, or we can say that IC is the heart of any modern electronic circuit. Without IC, we cannot imagine the electronic circuit. So some ICs are here. We have discussed the digital ICs, analog and mixed signal ICs. Now we are going to discuss about the historical perspective. So as the era of electronics started with the start of the solid state electronics, and the first solid state device is invented as a vacuum tube in 1987, which was invented by the J.A. Fleming. So this was the scientist who has invented the vacuum tube first. After that, in 1904, new vacuum tube was invented, which is developed as a which is known as triode, which is used for the amplification. So after that, in Bell Lab in 1947, William Shockley and some other scientists like John Bodin and Walter Bretton, they have invented the first transistor. So this transistor has replaced the vacuum tubes, because transistors are small in size and which is less bulky than the vacuum tube. So even consumes less power also. So after that, this transistor, after the invention of the transistor, some discrete circuits were invented. In this discrete circuits, some devices or some active and passive devices are placed by hand, means manually placed on the printed circuit board, and whatever the manipulations are there, it is physically only. So which consumes the power as well as some more space. So which is also called as non-integrated circuit. So after that, in 1958, Jack Kilby, who was the researcher in the Texas Instruments, so he has developed the IC, which is the integrated circuit, for which he has used some the semiconductor material as a germanium. So after that, Robert Noyce, who was the co-founder of Fairchild Semiconductor, he has invented the same, by using the same technology but using semiconductor material as a silicon, he has invented the first integrated circuit. So after that, after this first invention of the IC, the integration is level up from the SSI to the GSI, means from a small scale integration to the MSI, then LSI, which is large scale integration, VLSI, which is very large scale integration, then ultra large scale integration, giga scale integration. So this is continuously growing the IC technology. Now in between, Morse was the scientist. He has after his observation, he told that number of transistors on integrated circuit always will be double every 2 months or 18 months. So which leads to the increase in the processing power and performance at the lower current. And it was actually the true thing which happened after the invention of the first IC. So every 2 years, the density increases by the double, and this complexity also get increased. So this statement we recognized as a Moore's law. After that, we are going to study some main issues in the digital integrated circuit. So here I have written the 10 issues which manufacturer or designer mainly focus on, and we have to overcome these issues by using some technology. So the first issue is power consumption. So basically, ICs we often used in the portable devices and the battery power devices. So this to minimize the power consumption is the main issue which in the digital integrated circuit. So to reduce these power consumptions, designer needs to use some techniques. For example, clock gating and some power gating also. And third technique is dynamic voltage and the frequency scaling. So these are the some power reducing techniques we have to use. So in clock gating, what we need to do is we have to disable the clock whenever clock of the certain portion of the circuit which is not in the use. And power gating also. So clock gating is mainly reduce the dynamic behavior or dynamic power consumption, and power gating is basically for the static power consumption, in which we are completely off the circuit or some portion of the circuit which is not at all used. So in this ways, by using some techniques, we can minimize the power consumption. Now second is timing and synchronization. So timing and synchronization is very much necessary because if you want to avoid some errors, then it is very essential to have this timing of the timing and synchronization to be very correct. So because there are some timing related challenges, for example, clock skew. Clock skew is nothing but the difference in the arrival of the clock signals, and this is the issue in which we are going to see the clock skew and propagation delay. So propagation delay is nothing but the how the signal is propagating through the input to the output or through the whole circuit. So these are the issues which we have to reduce in the timing and synchronization. So the next is heat dissipation. So whenever there is something operation is going on, IC always dissipates some heat. So we have to use some cooling solutions and thermal management. We have to reduce this heat dissipation. Otherwise, it will leads to the degrade the performance of the circuit. So next is signal integrity. Maintaining the signal integrity by mitigating issues like crosstalk. Crosstalk is nothing but the some undesirable interference because of the electromagnetic waves. So and the signal reflection, which is the important issues to ensure the reliability of the data transmission. So again, we have to take care about these two things in the signal integrity. Then testability and verification. So testability and verification, in which we are going to see that comprehensive testing and verification are very important to identify the flaws. Means if any errors are there in the circuit, before manufacturing we have to detect that errors and we have to correct that errors. So by using some formal verifications and some simulation techniques also, we can reduce that issues. So after that, scalability is another issue. Scalability means as the ICs is going to have billions and billions of transistors, so it will shrink the size of the IC. So we need to, so in this, whenever the density increases and the components in the IC increases, some issues have been raised like leakage current and some different process variations. So we need to take care about these smaller whenever we are going to have more transistors and more active and passive devices. So we need to take care about the leakage current. So then design complexity is again the same thing, that we are mounting billions and millions of transistors. So it will increase the challenges for the complexity of the device, and we have to use some advanced design tools to reduce that complexity. Then eighth one is intellectual property integration. Means this is the third party integration. If someone want to use some intellectual property block from the another vendor to use it in their own circuit, so that also they can use, but there are some issues, means compatibility issues are there, so they need to take care about that. So this is also the one of the major issue in the digital integrated circuit. So after that, manufacturing constraints means some designing rules, and we have to be take care. For example, feature sizes, wire lengths, and some metal layers restrictions. So in this manufacturing countries, we have to take care about the all hardware parts. So yield and reliability means this is nothing but the final IC product in which we are going to see some defects and failures can be significantly compact on the cost and the performance. So these 10 issues are there, and we have to overcome these issues by using some different technologies. Now this one is the on which basis or which parameters we have to take care for to improving the quality of the digital circuits. So here some quality matrix are there in which we have to see that how the quality matrix depends. So the first quality matrix is nothing but the cost of integrated circuit. So there are two types of cost. First is the fixed cost, and second one is the variable. So fixed cost we can call it as non-recurring, and variable cost. So fixed cost is nothing but called as non-recurring, and variable cost is nothing but recurring. So on which factors these costs are dependent or independent, that we are going to see. So fixed cost is nothing but the whatever the efforts we are taking on the time and manpower. So it is completely independent of what are the sales volume and how much product has been sold. So this is completely independent of these two issues. So only we are taking only consideration we are taking is efforts in time, what is the time required for completing the ICs, and how much is the manpower required. So second second parameter on which the cost of integrated circuit depends is nothing but the uh, second time in which variable cost, which is nothing but the recurring expenses. So these are directly attributed to the manufactured product, means this will depend on the what is the volume of the product, what is the volume of the cell, and number of products sold. So this cost includes the cost of parts in the product, then whatever the assembly cost, we have to assemble the different components. So assembling cost is also there, and after manufacturing, whatever the testing we have to do, some manufacturing and functional testing we have to do. So in that also this cost will depend. So whatever the total cost of the IC is nothing but the summation of these two parameters, fixed cost and variable cost. So this is the first quality matrix. Second quality matrix is nothing but the functionality and robustness. So on which parameter the functionality and robustness depends. So this first is electrical behavior is the first parameter which can affect the functionality and behavior of the circuit. So second is nothing but so any electrical behavior means any wiring issues are there. So that will depends on, and any variations in the electrical circuit will definitely affect on the functionality and behavior of the circuit. Second is if there is any variations in the manufacturing process, that also leads to the unexpected response, or which can affect the expected response of the digital circuit. Will not get the proper response at the output if there are some variations in the manufacturing. So after that, third and major parameter which can affect the functionality, which is nothing but the disturbing noise. So if there is a noise present in the circuit, again it will leads to the some deviation from the expected output. After that, there are some two behaviors, that static behavior and dynamic behavior. So basically, if we want the circuit to be robust, then we have to see that static behavior of the gate, which is going to measure the robustness of the circuit, means how robust it is with respect to the variations. So even if the variations are there, it will give you the proper output and response. Then if you want to check that electrical function of the gate, is it properly functioning or not, so then it is we have to express it by the VTC curve, which is nothing but the voltage transfer characteristics. So it will plot the output function as a it will plot the output voltage, means V out, as a function of V in. Okay, so so VTC curve plays a very important role here. The next parameter is which affect the functionality is nothing which measures the functionality and robustness is nothing but the noise margin. So noise margin is nothing but the level of the margin which can sustain if the gates are cascaded, and here it is the high noise margin and low. So if I want to calculate the noise margin high noise margin, which is nothing but the VOH minus VIH, means VO is nothing but the output voltage, high output voltage, minus high input voltage. And if I want to calculate the low noise margin, the formula will become VIL, which is the input voltage, which is low input voltage, and minus VOL, low output voltage. So basically, if we want to represent the high voltage output voltage, we will represent it by 1, and if I want to represent the VOL, we will represent it by 0. So steady state parameter of gate measures how robust the circuit with respect to variations in the manufacturing process as well as the noise disturbances. Then the another one parameter is noise immunity. So noise immunity is nothing but the how system will withstand even if there is a presence of the noise. So basically it expresses the ability of the system to process and transmit the data or information correctly in the presence of noise as well. After that, it indicates that how system is immune to the noise. Then another is directivity. Directivity property requires the gate to be unidirectional. In the sense, even it should give the output whenever there is some transitions in the input. Otherwise, if there is no input given, it should not give the output. So that means it should be unidirectional. So we can get the output whenever there is activity in the input, otherwise not. Another quality matrix is nothing but the fan in and fan out, which is again related with the functionality and robustness. So fan is nothing but the how many number of inputs. These are the inputs to the gate. So this is the one gate. This is the fan out. So this is the gate, and how many inputs are there we are going to give. That is nothing but the fan in, and fan out is nothing but the how many gates are driven by the this particular gate. So this gate is nothing but the driving gate, and some load gates are connected to this driving gate. So fan in means number of inputs to the gate, and fan out means number of load gates that are connected to the output of driving gate. So this also this is also the important parameter which indicates the functionality. The next one is performance. So this also quality matrix is important, in which we are going to see this performance is we can expressed as a clock period or the clock frequency. So if there is a clock skew or any other errors or parameters are there, then we cannot get the proper performance of the circuit. Another one is power and energy consumption. So this power and energy consumptions means it will determine that how much energy is consumed whenever the operation is performed by the IC. So how much energy that IC consumed, and another is how much heat is dissipated by the IC. So whenever there is some activity is going on in the IC or any circuit, so it will dissipate some heat. We have already discussed, and for that particular case we have to see we have to use some techniques which can reduce the heat dissipation, or we have to use some cooling agent or cooling measures or techniques to lower the heat dissipation. So these are some quality matrix we have discussed here. So in the next lecture we will see the fabrication process of MOS, NMOS, PMOS and CMOS. So in CMOS also 3 different types of fabrication process are there. We are going to see that, and after that we'll see some stick diagrams and layout. So for today's lecture, these 3 topics we have completed. Thank you so much.